Okay, so today we're going to be talking about what's called moment of inertia. So we talked about last week that we called it a moment arm or a lever arm, and moment means the ability to move. So the moment of inertia is going to be the ability to start or stop rotational motion. So we're going to be talking about just generally the word inertia means the ability to stop any motion. So if you're running really, really fast and you're a light mass, it's easier for you to stop suddenly than if you're in like a big, huge truck with a larger mass. So we know that mass has an effect on whether you can start or stop something moving. So a big truck takes a lot harder, it's more effort to take a large truck to get it to start moving from a stop position or to stop it from a moving position than a lighter truck. Well, now we're going to be talking the moment of inertia, which is going to be basically the same thing, but instead of a start and a stop in a linear direction, we're going to be talking about start and stopping rotation. Okay, so it's the ability to start or to stop any sort of rotational motion. Okay, we use the symbol I, so the moment of inertia just stands for I, and that is going to be equal to the mass of the object times the radius of, or the distance it is from its axis of rotation, and then we're going to square that. So moment of inertia is the mass of the object times the distance from the axis of rotation, and we're going to square it. So here's an example. If you have a person, and a lot of times this is known for like in ballet dancing or ice skating, you'll see the ice skaters that'll be coming and their arms will be out, and then for them to rotate, they bring their arms in. And the reason why people do that is that you're decreasing the radius. So that if this person is going to rotate about its center right down here, this radius is larger here. Once you bring your arms in, your radius decreases. So you're going to go from a larger radius to a smaller radius, and that's going to create something to move, and this is the axis of rotation. So this is the same thing here. If I take a barbell and it has two masses on either side and I were to spin it around right in the center, it's going to feel different, and we'll do some experiments tomorrow where you'll be able to feel this, but it's going to feel different than if I try to rotate it around this axis and have this bar coming around like this. So that's what we're going to be talking about, is the moment of inertia. Okay, well, in the objects that I showed you before, they were mass particles, but we also have larger solid objects that will rotate as well. So this would be like a hoop, like a bicycle or a hula hoop, and we're going to be talking about, well, how does that rotate around? Well, a hoop rotating around the center is the mass of the hoop times the radius of the hoop squared, and that's what the value of I is. Now here, if we have a cylinder, so now this has height here and it's solid, the cylinder is going to be 1/2 the mass of the cylinder times the radius of the cylinder squared. And these are all given to you. I'm not expecting you to memorize them, but you do need to know when to use them and how to use them. So this is a sphere, so this could be like a basketball, a solid sphere, so it would be filled in, so more like a bowling ball. And the ability of a bowling ball to roll or to stop rolling, the I value is going to be 2/5 m, the mass of the solid sphere, the radius squared. And then here would be a long rod or a bar. So this could be like a 2x4. Say you're carrying a piece of wood, a 2x4x8, or the tracks that we were using for the collision lab, which would be a long, thin bar. Well, the moment of inertia about the center, so if you're carrying it at the center and you were going to twirl around with it, is going to be 1/12 the mass of the bar times the length of this bar squared, not the radius, so we're not talking about half, we're going to be talking about the full length of the bar. And these are things that you would be given, but you need to know when to use those. So let's try an example. Okay, we have this object here, and it's set with 3 particles. So we have a rigid rod right here of negligible mass. The reason why we don't count the mass is then we would have to take the moment of inertia of that as well. It lies along the y-axis. It connects 3 particles. So we have particle 1, particle 2, and particle 3. The system is rotating about the x-axis, so it's going to be kind of going in and out of this, the board right here. It's going to be rotating in this direction. We want to know, what is the moment of inertia of this system? Well, the way we figure the moment of inertia is the same way that we figured out the torques and the same way that we figured forces out. We can just add them up. So if I can find the moment of inertia of this object, and then the moment of inertia of that, and then that, I can just add all three of them up and we can get the total moment of inertia of the object. So let's look at the moment of inertia of this one right here. So the moment of inertia of the object 1 is just m1 r1 squared. Well, m1 is 4 kilograms. And now r is the distance this object is to its axis of rotation, and it's rotating around the x-axis. So the distance from here to here is 3 meters. And we're going to square it. Okay, so that's going to be 4 times 3 squared, so 4 times 9, which equals 36, and the units are kilogram meters squared. And there's no nice unit, it's just kilogram meter squared. Now we're going to find the moment of inertia of the second object, so I2. That's going to be this object right here, which is going to be m2 r2 squared. Well, m2 is 2 kilograms. And r2 is the distance from that object to its point of rotation, which is -2. But remember, we're squaring it so that negative goes away, so it really doesn't matter what side that the object is on of the axis of rotation. So it's 2 times 2 squared, 2 times 4, so we end up with 8 kilogram meters squared. Okay, and now we're going to find our third object, and that's this one down here. So it's going to be m3 r3 squared. Well, m3 is 3 kilograms, and r3 is the distance from here to here, so it's 4, 5, 6, and it's negative. Okay, but when we square the negative, we get rid of this, so it's 36 times 3, which ends up to be 48 kilogram meters squared. And then all we have to do is add them up. So you can see the summation thing, the sum of all those i's, or I net, is 48 plus 8 plus 36, and we end up with 92 kilogram meters squared. So this is the moment of inertia of this whole object altogether. Okay, well, we only have one example today. What you're going to be doing for homework, and you're going to enter this on the Edline assignment, I'm not going to put the question up there again, you just have to answer it. But what you're going to be doing is you're going to rank the following of these objects in order of the largest to the smallest moment of inertia. So there's really no value in here for us to figure out, but you're going to have to well, you can actually calculate it. If all of these have mass of m and the distance here is L, you're going to find out the moment of inertia about this object rotating right about its center here. Then you're going to find the moment of inertia of this object rotating here, and the distance here is L. And then this object rotating at this axis, and then this object rotating at this axis. So I want you to find they all have the same masses, each of these balls, which will have mass m, and they all have the same length L, 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 and then this one is L over 2 from the axis of rotation. So what you're going to do is you're going to find their i's, and you're going to rank them the largest to the smallest. And so you'll enter that in the Edline assignment in the order that they go in. And that's all we're going to have for today. So don't forget the assignment, and we will see you tomorrow in class.